Okay, we'll get started. So today we're going to venture into chapter 6. And chapter 6 is all about probability distributions. Okay. And the idea behind a probability distribution is that we are conducting a random experiment. We do a random trial, and at the end of the random trial, we record the outcome, and the outcome is recorded as a number. Okay, so these create something called random variables. So random variables are outcomes to random experiments. And the outcome is recorded as a number. Is a number. Either the outcome is a number or it's recorded as a number. That's kind of the idea behind a random variable. So before, we used to say, you know, we could talk about flipping a coin and we'd say, what's the probability that it lands heads? Or what's the probability it lands tails? Well, we could turn that into a random variable by saying we're going to flip a coin. If it lands heads, we write down 1, and if it lands tails, we write down 0. Now suddenly you have a random variable. Okay, so let me just give you kind of some examples of random variables. And we'll say, you know, you flip a coin, and if it lands heads, record 1. And if it lands 0, record 0. I'm sorry, if it lands tails, record 0. Okay, and then that becomes a random variable. Other examples of random variables would be you arrive at a bus stop at a random time. And we record how long you have to wait for the bus to arrive. Okay, and so there you have a random experiment or a random trial where you arrive at the bus stop at a random time, and then the thing that we are recording is a number. It's how long we have to wait. Or another example of a random variable could be you select a person at random. Okay, so you select a person at random, and then you record the height of the person. And so these are examples of random variables. And when we look at something like this, we might want to ask, you know, what is the mean value that we might see? Or what is, you know, we might have questions about this. And in order to answer some of these questions, we will want to be able to represent the probability distribution of the random variable. Okay, so we need to we need to be able to represent, how likely or unlikely particular values are. Okay, so we need to be able to represent how likely or unlikely particular values are, and in particular, we call this representation, this is the probability distribution of the random variable. How likely or unlikely certain outcomes are. This is the probability distribution of the random variable. All right, so let's take a look at each of these that I've kind of mentioned as examples of random variables. All right, so the first one is flip a coin. If it lands heads, record a 1. If it lands tails, record a 0. Okay, so this, put this right here. And so this is what we call an example of a discrete random variable. Discrete meaning only certain outcomes are allowed. Okay, and in this case, only heads or tails or 0 or 1 is allowed. Okay, so only certain outcomes are allowed. Okay, and so in this case, we can have 0 or 1, and what is the probability of getting 0? So we're saying we flip a coin. If it lands heads, we record a 1. If it lands tails, we record a 0. So what's the probability of getting a 0? 0.5. Okay, not a trick question. It's 0.5. And then a probability of getting a 1 is also 0.5. Okay, and so to represent this with a picture, we say, okay, well, here is 0, here is 1. We can also have a 2 and -1 and whatnot, but effectively the only values that matter are the 0 and the 1, and these will have heights at 0.5. And we draw a dot right here and a dot right here, and we say, well, and that's our probability distribution. 0 has a probability of 0.5. 1 has a probability of 0.5. Okay. And we might, in some pictures, you might see a vertical line to kind of, because dots might be hard to see, you might see a line going up like this. But it's effectively the same. This is just to say that 0 has a probability of 0.5 and 1 has a probability of 0.5. And this is the discrete case where you have particular outcomes are, only particular outcomes are possible. All right, is this diagram, does that make sense? Okay. All right. In this chapter, however, well, that's not true. Okay. In the beginning, we're going to start dealing with continuous variables first, and then we'll come back to the discrete case. And so we might, let's take a look at the other one. You arrive at a bus stop at a random time, and we record how long you must wait for the bus to arrive. Okay. So let's say at the bus stop, the bus comes every 20 minutes. Okay, we'll say the bus comes every 20 minutes. Right. And okay, so if the bus comes every 20 minutes, and we're arriving at the bus stop at a random time, what is the least amount of time we would have to wait? 0, right? We might be super lucky. We might get to the bus stop right as the bus is arriving. We have to wait 0, right? So kind of our minimum wait time bless you, is 0. And what is the longest we would have to wait if we arrive at a random time? Our max wait time would be 20, right? And every value in between 0 and 20 is equally likely, right? Do we agree with that? If we're just arriving at a random time, every value between 0 and 20 is equally likely. Okay. And so the way we represent this is we say, okay, we can go from 0 to 20, and then we say every value between 0 and 20 is equally likely. And so all the numbers between 0 and 20, they get the same height on my probability distribution. And technically, values below 0, they are right here at 0. And then values above 20, they have also a probability of 0. Okay, so there's no possibility of waiting over 20 minutes. And then between 0 and 20, this line is the same height. Okay, the flat line means all of these values are equally likely. Right. And so with this is also a representation of the probability distribution. And one thing to note for continuous variables, okay, when we have a continuous random variable, which is what we have over here, is that over here, if we shaded the entire region underneath the probability distribution, or we might call it a probability density, if we shade this entire area, the entire area always equals 1, okay? The area of the distribution always equals 1. Area of the distribution equals 1. So if I said, what is the probability that we have to wait over 10 minutes? Represented by drawing a line at 10 and then shading in the region above 10. Okay, I said, what is the probability I have to wait over 10 minutes? You would tell me that this area is 0.5, right? And therefore, the probability we have to wait over 10 minutes is 0.5. Okay, so this area equals 0.5, which means the probability of wait over 10 minutes is equal to 0.5. And so this is kind of the idea that we're going to work with when we are talking about the normal distribution. Okay, so the big idea here is we've got a curve or a line that represents our probability distribution. Okay, so in this case, the flat line means that all of the values between 0 and 20 are equally likely. And with the normal distribution, our probability distribution looks like a hill. Okay, something like this. It's supposed to be symmetric. And so what we see here is that values kind of near the middle. Values here values near the middle are most common because the hill is the tallest near the middle. Okay, the line, the curve, values near the middle are most common. These appear the most frequently. Whereas values out here and over here, these are less common. Less common values, as represented by the fact that the curve is near zero. Okay, the curve is close to zero. And so an example of the normal distribution could be something like, you know, in the United States, if we're looking at the heights of adult women, we can say that the distribution will look somewhat like the normal distribution. Okay, so here's an example. Is, you know, we select a random woman from the United States. We record her height. Okay, and the heights will look somewhat like a normal distribution. And for simplicity, we'll say that the mean height will be something around 5'4". Okay, maybe something around there will be, we'll just say about 64 inches. Okay, just for simplicity, we'll call it 64. And the standard deviation just for simplicity, we'll say is 3 inches. Okay, so we'll say the mean height will be 64, the standard deviation is 3. And so what, you know, that means in my normal distribution, I could put 64 in the middle, and heights near 64 inches, so 5'4", so, you know, 5'3", 5'4", 5'5", those are going to be kind of your most common, most frequent heights that we might observe for adult women in the United States. Okay, and then heights that are much higher or much lower than that also exist, but are going to be less common. So if we're at 5'4" and we go up 6 inches to 5'10", okay, that's going to be less common than values around 5'4", 5'5", 5'3". And then if we go down 6 inches to, you know, say 4'10", will also be less common. Those heights will be less common than values near the middle. That's kind of what we have. Okay, so with the normal distribution, if I said the mean is 64 and I want to know, okay, what percentage or what proportion of women are taller than 64 inches, you would tell me what? So if I draw a vertical line at 64 and I say, what proportion are taller than 64, you would say 0.5, right? Okay, not a trick question. Okay, so what proportion are taller 64 inches, we would say, okay, 0.5, half. If the mean height of women in the United States is 64 inches, then half, about 50% of women in the United States are taller than 64 inches, if they indeed follow the normal distribution. Okay. What do we do if we ask other questions? You know, what proportion of women are taller than 65 inches or shorter than 62 inches or something like that? Well, those types of questions are a lot harder to answer. And so before we can start to answer those, we have to understand the standard normal distribution. Okay. So the standard normal distribution I'm struggling with drawing these normal curves. Hardest part of my job. Okay, so we'll say this is our standard normal distribution. The mean for the standard normal is equal to 0, and the standard deviation is equal to 1. This is the standard normal distribution. And so if I said, you know, if I were to draw a vertical line, and this is also called the z distribution, by the way, the z distribution. So I can say, you know, I draw a vertical line at z, vertical line at z equals to 0, okay? And I shade to the left. So imagine drawing a vertical line at 0, and we shade everything to the left. How much have I shaded? Okay, and your answer there is 0.5, right? Because 0 is right there at the middle. If I draw a vertical line at 0 and I shade everything to the left, the amount I have shaded will be 0.5. Okay, so this is where our tables come in. All right, and so some of you got here a little bit late and you might not have picked up a table. If you don't have a table, come forward and grab a table from, I don't know, whatever this station is up here. Okay, and so what we can say is, you know, I draw a vertical line at z equals 0. I shade to the left. How much is shaded? Another way of saying this is, what is the probability that z is less than 0? Okay, and let me pull up my table on the computer here. Okay, so if you flip to the positive side of the table, you'll see in the top right corner, or top left corner, we see z 0.0 and 0.00. We see the number there is 0.5 or 0.5000. Okay, so you know when I say z is equal to 0, I can also say that's the equivalent of z is 0.00. And when we look this up in the table, we go to the row. The row is going to be 0.0, and then the column is going to be 0.00 to indicate we are at 0. So we're at, in the row 0.0, and the column 0.00. This is kind of what your table looks like, 0.0, and the column 0.00. And the number there is 0.5000. Okay, so we just look at the intersection of these two things. And so therefore, my area is 0.5000 or just 0.5. If I draw a vertical line at 0 and I shade everything to the left, the amount I have shaded is 0.5. Is that okay? All right, and so you know if I draw another curve, So let's say, you know, here's another curve, standard normal. We're centered at 0. This time, I'm going to draw a line at, we will say 0. I don't know, 6, 7. 0.67, okay? And so z is equal to 0.67, and I can ask, what is the probability that z is less than 0.67? So the fact that I have less means we are shading to the left, okay? We want to know what is the probability that I end up less than 0.67. So we go to our table, so we go to the table, and we go to the row 0.6 and the column 0.07 to make the numbers 0.67. Does that make sense? We're going to go to the row 0.6 and the column 0.07. And what is the number that we find there? Okay, so yeah, we go to the row 0.6 and the column 0.07, and we find that that number is 0.7486. 0.7486. So, you know, you go to the column 0.07, 0.6, 0.7486. This is kind of our intersection right there. So that means the area to the left of z equal to 0.67 is 0.7486. Is that good with everybody? Okay. And so if I ask, okay, what is the area to the right? To the right of z equal to 0.67. Okay, so this would be akin to shading to the right of 0.67. Okay, and I'm asking basically, you know, how much is shaded in yellow? And you would tell me, how do I get this number? Subtract 0.7486 from 1, because we know the total area under any probability curve is equal to 1, so we know that the area to the right has to be 1 minus 0.7486, and so therefore I get 0.2514. So my area to the right is equal to 0.2514. So it's a matter of looking up your z-score, and the table will always give you the area to the left. Maybe that's worth putting. Table always gives the area to the left of z. And so therefore, if you want the area to the right of z, you have to subtract that from 1. Oh, actually, in fact, it says that right there on the table. It says cumulative probability for z is the area under the standard normal curve to the left of z. Okay, so there you have it. So the table always gives you the area to the left of z, and that's what we have. Okay, so let me, I'll give you a little clicker question practice thing, and we'll try this out. And so I will ask, all right, what is the shaded area? Okay, so your answer choices are, let's see here. Okay. Where's my clicker software? Okay, let me get the clicker software fired up here. Okay, so the poll is open. You can go ahead and get your clicks in. Whoops. All right, let's take a look. All right, okay. It looks like most of you guys got it. That is correct. Our answer is 0.9192. So, some of you guys did not get that right. And so what we do is, our z is equal to negative 1.40, which means we go to the row. The row is going to be negative 1.4. And the column to make up will be 0.00. Okay, so we go to our table. We have to go to the negative side. We go to negative 1.4 and the column 0.00. And the number that I see there is 0.0808. Okay, that is the area to the left. The area to the left of negative 1.40 is 0.0808. However, the shaded area that I have is the opposite of that, right? So here, this side is going to be 1 minus 0.0808, and that is equal to 0.9192. Okay, so our shaded region is 0.9192. I'm going to just write a quick shortcut, and you don't have to use this if you're not comfortable with it. Okay, the shortcut is the area to the right of z is equal to the area to the left of negative z. And that's because the table is symmetric. So if you want the area to the right of negative 1.4, you can find the area to the left of positive 1.4. Okay, that's a little shortcut. If you're not comfortable with that, don't use it. Okay, just stick with look up the area to the left and do 1 minus that. Okay, that's much more safe and that works. But sometimes students will notice this on their own and ask about it. So I do want to say that yes, it does work out. Okay, that the shortcut, the area to the right of z is equal to the area to the left of negative z. But just like any other shortcut in life, you should only use it if you're comfortable. Okay, so we've been dealing with the standard normal, and I said, well, this can be used for questions such as what proportion. So if we go back to U.S. women's height, okay, and we said normal distribution, the mean is equal to 64, and the standard deviation is equal to 3. So if we say something like this, normal distribution, mean is 64, standard deviation is equal to 3, we could ask a question such as, what proportion of women are shorter than, let's say, 5'6". Okay, so 5'6" would be 66 inches. So what proportion of women are shorter than 66 inches? Okay, so if I draw a picture, in the middle we're going to put the mean 64. Okay, and then 66 is bigger than 64, so that goes to the right of 64. And now I want to know what proportion of women are shorter than 66 inches. So this is kind of my setup. Right. Do you guys remember z-scores back from chapter 3? Okay, what was the definition of a z-score? Yeah, the number of standard deviations we are from the mean. Great, okay. The z-score is the number of standard deviations we are from the mean. Okay, and the way we find that is we take our x and we subtract off the mean and we divide by the standard deviation, right? That's how we did it. Okay. When we're talking about normal distributions, the mean we use, the symbol looks like this. It looks like the letter U, but with a line in front, and it's pronounced mu. Okay. And the standard deviation looks like this. It looks like an O with, I don't know, a line, and it's called sigma, all right? These are like Greek letters. And so, we might say z is equal to x minus mu divided by sigma. And so in this case, we're going to turn 66, convert 66. Step 1 will be convert the measurement 66 to a z-score. So I say z is equal to 66, that's my measurement, minus the mean, which is 64, divided by the standard deviation of 3, and I get z is equal to 2/3. I get 0.66667, okay? That's step 1. We've converted 66 into a z-score, and I get, 0.66666. I need to look this up in the z table. So now we look up the z in the table. Now the problem is that the z table only gives us 2 decimals of precision. So we always have to round to 2 decimals. Okay, so look up the z in the table. Okay, after we round to 2 decimals. So we round to 2 decimals. All right, so we're going to look up z equal to 0.67. And when I do this, I go to the row 0.6, I go to the column 0.7. Oh, coincidentally, we had looked up this number earlier. And the number that we find is 0.7486. Okay, so the area to the left of z is 0.7486. Okay, and that's our answer. What proportion of women are shorter than 66 inches? That answer is around, about 3/4. 3/4 of women, according to this normal distribution, are shorter than 5'6", approximately. Is that okay? All right, let's try out in our last couple seconds. Let's try out an example. Yeah, I'll actually have you guys work through it, but we won't make a clicker question out of it. Okay, so let's say, I don't know, I'm making up. We'll say for a certain breed of dog. I don't know. Yeah, okay. So for a certain breed of dog, we'll say the mean weight is, I don't know, 40 pounds, and the standard deviation is 5 pounds. Okay, I don't know. Is that like? I'm just making stuff up here. Okay, so we'll say what proportion of dogs of this breed weigh less than, we'll say, 34 pounds. What proportion of this breed weigh less than 34 pounds? Okay, go ahead and try to work this out. You guys have like a minute. and then we'll go over the answer real quick. So the first thing you want to do is get a z-score. All right, maybe I'll just give you the answer here. Okay, so step one, find the z-score, right? So we're going to do 34 minus the mean, which is 40, and we divide by the standard deviation, which is 5. And so I get a z-score of negative 1.2, right? Negative 1.2. And then the next part is I look up z is equal to negative 1.2. The column is 0, right? Negative 1.20, and the value that I find there is 0.1151. Okay, so we look up z equal to negative 1.20, and the area is 0.1151. This is my area. Area to the left, 0.1151. Okay, so that's our answer. All right, well, we'll end there. We'll see you guys on Friday.